Hello everyone, my name is Alexis Nolin-Lapalme, and today I'll be presenting my work called PrivECG joining PrivECG for end-to-end anonymization. It must be known that currently in the clinic, anonymity is obtained by removing certain type of metadata, things like name or address of the patient. However, the data itself can be highly descriptive. Let's take an extreme example, head MRI or CT scans, which contain the face or the shape of the face of the patient, which can be easily reconstructed and thus allow easy identification of the patient without ever seeing the metadata. This can be done, although differently, with other types of data. For example, the electrocardiogram. Electrocardiogram is basically when we put electrodes on the chest of a patient and monitor the depolarization or the passing of the current through the heart muscle. Here we have an example of a 3-lead electrocardiogram, although it's usually 12 lead in the clinic. This allows us to generate waveform like these that allows us to monitor things like heart rate or diagnose various types of diseases. However, in the last few years, we've been able to find that more information can actually be obtained using the ECG. For example, the sex of the patient. Here, although stylized, you have the information, or you have the waveform of a female and a male, and you see the male usually have a much higher R wave, which represents the contraction of the ventricle. This allows us to quite readily build convolutional neural network that taking that ECG and predict the sex. Here, we obtain an accuracy of 88%, but this can go as high as 97% on other types of data sets. This begs the question, can making the sex on the ECG ambiguous using generative approach help preserve the identity of the patient? To do so, we propose a GAN, which is the architecture of the UNet for the generator that takes in the ECG of the patient and generate E prime, which needs to be similar to E, however differently enough that when fed into the discriminator is unable to predict the sex of the patient. And hopefully at the end, E primes are very similar to E, but slightly different to allow the anonymization of the sex-linked features. To help us do that, we use a variation of the mean square error where we segment the region in green and in red. So in green, we want to weigh those regions a little bit more to have better reconstruction. However, in red, we want to have more variation. This is the R wave, which is a key differences between sexes. What we want to have as a result is we have here in green, we have the inputted ECG waveform. In orange, we have our approach with classical mean square error. In red, we have our approach with a variation of the mean square error and two comparative approach. And we see that we preserve some of the shape, however, we'll have a lot more variation into the waveform. To quantify this in terms of privacy and utility, we use the equal error rate. Briefly, a highly descriptive modality has a very low false acceptation rate and false rejection rate as the identification errors are quite low. Thus, the EER is very close to 0. However, a private modality has a false acceptation rate and false rejection rate that's much higher, though the equal error rate is much closer to 0.5. Thus, in our results, we see that PrivECG here, when used to predict the sex, is much closer to 0.5, so very hard to identify the patient's original sex. However, the ER is much higher than the others, so high privacy, while the F1 score on disease prediction task is very high, allowing us to produce a high level of utility while being private. I want to thank my entire team, and if you have any questions, please contact me by email. Thank you.